Okay, section 5.5 is all about negative exponents and scientific notation. So this is a bit of a departure from what we've seen in the first 4 sections of this chapter, but bear with me, it is actually linked. So we're going to be dealing with negative exponents a lot when we start dividing polynomials, which is hint hint what we're doing in the next 2 sections. So we want to have a good foundation about the negative exponents as well as regular positive exponents. To be clear, nothing in this section has to do with polynomials specifically, but there is some application that we'll see. So we have 4 objectives in this section. The first is to simplify expressions with negative exponents. Our second objective is to write numbers in scientific notation. And the third objective, which really is just basically 2b in this case, is to convert from scientific back to standard form. Excuse me. And then finally, we're going to look at how do we actually do some arithmetic or operations in scientific notation. So we'll get to the scientific notation stuff in a bit. Let's start with negative exponents. So if a is a real number other than 0, 0 is the only number this doesn't work for, and n is an integer, then a to the negative n is equal to 1 over a to the n. And 1 over a to the negative n equals a to the n. So essentially what a negative exponent does is it looks at your integer, your real number, whatever it is, as a fraction, either over 1 or under 1, depending on what form you have, and then flips it. So if you start with a fraction that is over 1, like this, and you have a negative exponent, it pushes this piece to the bottom and flips the 1 to the top. Alternatively, if you have a fraction that's under 1 and you have a negative exponent, it pushes this piece back up to the top and puts the 1 underneath. And remember, everything can be thought of as divided by 1 and not change its value. So we just got a few examples here, simplifying some expressions and then simplifying a couple more below that are just a little bit different using our laws of exponents. So in a, 3 to the negative 2, according to our rule here, says that this is 1 over 3 squared, or just 1 over 9. And again, this right here is an intermediate step that a lot of people are going to start skipping as they get more comfortable. But it's an important step to understand when you're first getting used to this or reacclimating yourself to using negative exponents. B says we're going to take this and put it on the bottom, so 1 over 2x quantity to the negative 3, and now we can, or to the positive 3, sorry. And now we can apply our exponent rules and distribute the third power, and this is 8x cubed on the bottom now. Part C is a little bit trickier. This is 1 over 2 plus 1 over 4. And so this is 2 over 4 plus 1 over 4, getting a common denominator between the 1/2 and the 1/4. And so this is 3/4 as our final answer. D, again, is trying to trick you, but not in the way that you may be thinking. The parentheses are on the negative, so when we put it to the bottom, the whole thing, including the negative sign, comes down. And we have negative 2 to the 4th, which of course is going to be 1 over 16, since it's an even power. negative 2 times negative 2 times negative 2 times negative 2. And then finally over here in E, this just pushes variables to the bottom just like that, and there's nothing else we do when we have variables. But E is setting up the next three below here, where we're now going to be doing more with variables and simplifying. So you can do this one of two ways. You can use your negative exponent rules first, or you can use the exponent rules that we saw in 5.1 first. It doesn't actually change anything. So I'm going to show you on part A how we could do just negative or just exponent rules first. So all the regular rules apply distributing. So this is y to the negative 3 to the negative 6 times z to the 6th to the negative 6. This is still exponent raised to exponent. We still multiply. So this is y to the 18th times z to the negative 36th, which then has to be flipped, y to the 18th over z to the 36th. And you could have done the negative 6 first. You would have had everything on the bottom, and then you would have had to bring the y to the 18th up. So now in B, we have a little bit more, complicated, where we need to do some simplification first. So we're going to multiply exponents, and we have 2 to the 4th, which is 16. X to the 3rd to the 4th is x to the 12th. There's a times x here. There's an x to the 7th. And so this is 16x to the 13th. And then the way that we think of this as negatives, to make our life a little bit easier, we bring the x to the negative 7 back up. And now we can clearly see that this is 16x to the 13 plus a negative 7, or just minus 7, or 16x to the 6th. Now this is just an alternate way to do our quotient rule. At this point we could have canceled 7x's from here and 7x's from here, just like we did in 5.1. This is just giving you another option, essentially. So now, in part C, we have a much more complicated version. What you want to do when you have lots of negative exponents is flip them all to where they're supposed to be. So the 4 to the negative 1 needs to come down. The 4 to the negative 3 needs to go up. The x to the negative 3 needs to come down. And the y to the negative 6 needs to go up. So I'm going to rewrite this as 4 to the 3rd y times y to the 6th over 4 to the 1st x squared times x to the 3rd. And that's pushed everything that's supposed to go back up or come back down according to their exponents properly. And now we can simplify. 1, 4 cancels with one of these, leaving 2. So this is 16 y to the 7th over x to the 5th. And nothing else will cancel, so that will be our final answer. Again, you can do the exponent rules from 5.1 first here and do, okay, I have negative 3 here and negative 1 here. But when you cancel the negative 1 here, you're actually not canceling a negative 1 so much as you're canceling a positive 1. So unless you remember that, you can make some small errors that affect your answer. Same thing here. You're canceling a negative 3 on the exponent, which is not what we did over here. So it's opposite of what I just said for variables. But you get the idea. I would recommend that you flip everything first and then simplify. It just makes your life a little bit simpler. And you don't have to worry about when does the negative need to be canceled as a negative, or does it need to be canceled as a positive, and so forth. So let's talk about scientific notation for a little bit here. So a positive number is written in scientific notation if it's written as the product of a number a, where a is less than or greater than or equal to 1 but less than 10, and an integer power r of 10. Now, why do we do non-negatives? Just because we typically don't look at really, really negative values. Excuse me. So what this looks like in practice is you usually see a times 10 to a power r like this, or a times 10 to a power r like this. You've been seeing scientific notation. We love to use scientific notation in things like chemistry and physics, because you get a lot of really, really big numbers, or alternatively, really, really small numbers, because this says integer power, so you can have tiny, tiny decimals if r is negative. So let's look at some examples of going back and forth between all the different types, from scientific to standard, from standard to scientific, and vice versa. So write the following numbers in scientific notation. Scientific notation, its one rule is that a has to be between 1 and 10. So you always just move your decimal place all the way to right here, 3.67. And then it's times 10 to how many places you had to move that decimal. In this case, there was 8 decimal places we moved. 1, 2, 3, 4, 5, 6, 7, 8. And that's our answer. This is scientific notation. With decimals like this, you're moving the decimal place to the right. So this is 3 times 10 to the negative 6. Now, just to kind of show you why this is a negative, think about what we just learned with the negative exponents. That means this is really 3 over 10 to the 6th, which means it's really 3 divided by 10, 1, 2, 3, 4, 5, 6. So it's a tiny fraction, which is what our decimal is, a tiny fraction. So that's how the negatives work. And then in part C, again, you just count. I always count by 3, so this is 3, 6, 9, 10. So this is 2.052. So even though A needs to be less than 10, it can have as many decimals as you have digits. So even if these were all zeros until this very last one here was a 1, you'd have 2.0000001. And then times 10 to the 10 in this case. And if you've ever thought about why do we have decimal place or commas after 3 decimals, it's to separate factors of 1,000 and also to make switching to scientific notation so easy. Because you just count 1, 2, 3, 1, 2, 3, 1, 2, 3, 1. Instead of counting by ones like we did here. So that's converting to scientific notation. Now let's talk about converting back from scientific notation into standard notation or standard form. It's really just undoing what you did. So this is 102, and my decimal is here, so I'm moving it 5 places. So at 102, I've already moved it 2, 1, 2, and then I just count 3, 4, 5, and then put in my correct commas. And if you're ever not sure, just put your number back into scientific notation. So this would be 3, 4, 5, and it'd be 1.02 times 10 to the 5th. So I know I did this right. In part B here, we have a 7, 3, 5, and an 8. And the decimal's here, and I need to move it to the left because it's negative. So 1, 2, 3. There's no decimal there. I just touched the paper with my pen. And so now, again, you can check your work. 1, 2, 3, 7.358 times 10 to the negative 3. Everything looks good. And then finally, this is 30007, and I need to move 5 to the left. So from 3, I go 1, 2, 3, 4, which means I have 4 extra zeros that need to get placed in here. And sometimes you'll see the 0.0. Some people like that format better. That's scientific notation. Again, it's just a shorthand so that you're not writing really, really long numbers. So imagine you had to write, this thing or this thing 7, 8 times in a paper that you were writing for a school, a report in chemistry or something, a lab report. It's much faster to type this out or to write this out than it is this one. And that's scientific notation really has died off because of computers, because in essence it's not that bad to just hit 0 key a bunch of times. But back in the day when there were no computers, this was a really easy way to shorthand things. So to finish up here, we're going to talk about performing operations in scientific notation. And this is supposed to be 10 to the 13th here. I believe yours should be fixed already. So because scientific notation is multiplication, we get all the properties of multiplication that we know and love. So I can rewrite a, which is 8 times 10 to the negative 6 times 7 times 10 to the 13th, as 8 times 7 times 10 to the negative 6th times 10 to the 13th, which allows me to use my exponent rules to rewrite this as 10 to the 7th and this as 56. Now it says write your answer in standard notation, so that means this is 5, 6, and then 1, 2, 3, 4, 5, 6, 7 extra zeros. This is another reason why scientific notation was used and still is used even though we have computers, is that you can do really fast multiplication for very big numbers when you only have a few digits in the front. You know, this is 80 million times, or not 80 million, this is a really, really big number with 7 at the front, and this is a really, really tiny number with 8 at the bottom, and you can use scientific notation to just make that multiplication easier. Same thing with division here in part B. I can split this, since it's multiplication, into 12 times 6 times 10 squared over 10 to the negative 3, because fraction multiplication would just be directly across the bottom and top. And so this is 2, using our exponent laws, this is times 10 to the second times 10 to the third, or 2 times 10 to the fifth. And then in standard form, that's 1, 2, 3, 4, 5 extra zeros, 200,000. Instead of actually having to divide that big, big number. So, scientific notation has its uses. Even today in the computer age, it allows you to do some things by hand very, very quickly without having to go to the computer. But it was used a lot to save space when writing things out by hand, because you don't want to have to write something that has 13 zeros in front of it every time. All right, so next section after this will be our second to last section, and we'll be dividing polynomials finally.